Hi, we're going to be talking about water cycle. I'm sure we're going to spend a little time about evaporation and condensation and precipitation and going into groundwater and all that stuff, but we're also really just talking about where is our water. If this is our Earth without the water on it, this is comparative in size. This is all the water on planet Earth. And compared to that amount of water, only 3% of it is drinkable. It's fresh water. Everything else here is 97% is salt water. So, of that 3% that's freshwater, 79% of it is found in glaciers and ice caps, which are melting. About 20% in groundwater. And then we get a little bit that's accessible on the surface in freshwater. And of that little bit that's accessible, 52% of that's in the lakes. Water within organisms is about 1%. Rivers is about 1%. Rivers are pretty transient. Water vapor is about 8%, and soil moisture is about 38%. So that's where our fresh water is located. And here is the ever present water cycle. So as we go through this, whoa, that's loud. Water starts to evaporate, and the sun heats it up. And as that occurs, we get evaporation, and particulates are in the air, and we can have condensation. Then it falls as precipitation, it falls in the land, and it can do runoff, or it can percolate through into groundwater. And that groundwater also, remember, moves laterally towards the lowest point, which if most places will be the ocean. And remember, it can fall as snow or rain or sleet or hail. So that ability for water to get through into the ground depends on how permeable that is, how easily it is for fluids to flow through something. So like this rock, it looks solid, but water can flow through it. So sometimes they'll actually make sidewalks that are kind of cemented together really loosely, but enough that we're sturdy for us, but allows the water to go through. Porosity then is how much space there is. So basically that's the pore space. So permeability is the ability for easily flow through liquids. Porosity is how big are those spaces that allows it to flow through. If you're really bored, you can go in, and this is an interactive thing on the pathways for the water cycle, and you can plant crops and all of that. Now I'm guessing I'm going to have to turn that volume up again.
All the water on Earth today, every drop, is all the water there has ever been on the planet. Fresh water is actually millions of years old, the same water flowing in a continuous loop, falling as rain and snow from clouds to the Earth's surface, running in rivers, pooling in ponds, flowing from faucets, irrigating crops, traveling through plants, generating power, eventually evaporating into the air and condensing into clouds again.
Why is there life on Earth? And the reason there's life on Earth is because Earth has this perfect water cycle.
The water cycle, so simple even small children understand the basics, yet so complex the most advanced Earth scientists, hydrologists, geologists, and biogeochemists are studying every part and process.
The water cycle is fascinating. It's something that's around us all the time, and yet we don't really understand it.
How to summarize what is known about the water cycle? With two words: flows and stores. The water cycle is a series of flows of water between various water stores or storages. Clouds in the atmosphere.
There's always a little bit of water in the atmosphere. We talk about relative humidity. It's a humid day, it's a dry day. Either way, there's water, sometimes a little, sometimes a lot.
There's a lot of water in the ocean, 70% of all the water on Earth. In the ice sheets and glaciers, 2/3 of all the fresh water on Earth. In the snowpacks atop mountains like the Sierra Nevada. In the Great Lakes, in rivers and streams, in reservoirs and watersheds, in wetlands, in the soil, in and on plants and trees rooted in the soil, and beneath the soil, in water tables and underground aquifers like the Ogallala High Plains, which runs underneath parts of 8 states from South Dakota to Texas. All this storage is temporary. Water in all its forms is always in flux and always moving. And there is a name for every kind of movement in the water cycle, starting with precipitation.
Precipitation is the process of water falling onto the surface of the earth. You can have precipitation in many forms: rain, snow, hail.
Rain is falling water in liquid form. Snow, ice, hail, and sleet are falling water in solid or frozen form. Fog and mist, falling water in gas or vapor form. Precipitation that falls directly onto the oceans becomes part of surface ocean and can be churned by wave and wind action into ocean currents. Rain and snow that falls directly on rivers and streams becomes one part of stream flow. Rain that falls onto land takes a different path to the river, as does the snow and ice that falls and collects on mountaintops when temperatures warm.
When snow melts, some of it runs through the snowpack and goes into small streams, tributaries that feed into large rivers.
What about that precipitation that falls on and over land? Some is intercepted by vegetation, plants, and trees.
Like you might imagine someone in a game of football intercepting the pass. These are raindrops trying to come to the ground, and the leaves on the tree intercept them before they hit the ground.
And the precipitation that does hit the ground, it can run off if the ground is hardscape, covered with asphalt or concrete, or if the soil is too wet or saturated to absorb more water, like an over-soaked sponge. Otherwise, precipitation infiltrates the soil surface, percolates into the ground.
Think of it as the water percolating through your coffee grounds in the morning. Gravity continues to pull it downward so it will move through.
Through the topsoil, spaces between soil and rock particles, down to bedrock and further into fractures, into deep underground aquifers. Even groundwater here is moving sideways or laterally, discharging toward a river, lake, or the sea. Generally, the deeper the flow, the slower the flow.
Some of that fractured water might take a very long time, thousands to millions of years to get out.
And how does water get back out into the atmosphere? It evaporates. It's turned from a liquid into a gas or vapor by the heat of the sun.
If you put a bit of water into a bowl and you set it outside on a sunny day, it's going to disappear. It's still water, it's just in the form of a gas rather than the form of a liquid.
Water evaporates from every wet surface, even from wet air. Some rain and snow evaporates into the air while falling. Water evaporates through our respiration and perspiration, and from plants through transpiration. Trans means through or across. Plant roots draw up groundwater.
And plants pull that water up through their stems into the leaves and then release it back out through evapotranspiration.
Evapotranspiration, a spelling bee-worthy term for evaporation from soil and water surfaces, plus transpiration from plants. Evaporated water molecules are tiny enough to flow into the air, mixed with smoke and dirt particles in the atmosphere, cool, condense into visible masses of water vapor, clouds. Winds move clouds into colder air, water droplets collide and merge, grow bigger and heavier, until they are so heavy they fall again, as rain or snow, sleet or hail. Precipitation, collection, runoff, interception, infiltration, percolation, discharge, transpiration, evaporation, condensation. The water cycle.
Okay, so we're going to keep going on. If you're wondering if you've noticed I have a very red face, it turns out when I went out to walk yesterday, I thought I better be good and put some sunscreen on, and I had an allergic reaction. So I have very red ears and very red face. So that's, if you're noticing it, that's why. Again, if any of these videos are hard to hear, go into the notes, watch the video on the notes, and then answer the question in Edpuzzle. So aquifer, she talked about that, the Ogallala. It's layers of sediment with porosity. So in other words, we let things through, but they also have something called a confining layer. So if we have a confining layer down here, that means the water can't really go down any farther. And if we have a confining layer in between, You can actually have like groundwater here and then a deeper aquifer here. Now, interestingly enough, if we dig a well here, it's about the same height as the water table, and you'll have to get a pump to pump it up. Some of you have wells at your house, so you have a water pump. There used to be along Highway 55, and they've capped it. If you can actually dig a well down into this confining layer, do you see that this is so much lower than up here? And remember, water always wants to find its own level. This is called an artesian well because they've actually punctured it. It's lower than the place where the water comes into it, and this will just flow out continually on its own. Where it's like take a bottle of pop, shake it up, and let it go. It's all going to come out. All this pressure above is just acting like that pop bottle exploding and coming out. So that's an artesian well. A regular well is one that you actually just goes into the water table, or it could go into an aquifer, but it's about the same height, and then you have to pump it out. An artesian well flows on its own accord.
In the state of Kansas, agriculture is king. Along with high yields of corn and soybeans, Kansas is the top wheat producing state in the U.S., with yields of more than 382 million bushels in 2012, according to the USDA. The secret to this land's bounty is not just the soil that covers it, but also something below ground that no one can see: the Ogallala Aquifer, the largest freshwater aquifer in North America.
For decades, we've had incredible production of agricultural crops on top of this, and largely that's because of the incredible water resources that have been available to it.
The Ogallala Aquifer, also known as the High Plains Aquifer, is a groundwater storage reservoir that stretches 174,000 square miles underneath parts of 8 states, from South Dakota to Texas.
This well here is 303 foot deep.
Stan Townsend, a 6th-generation farmer from Weston, Kansas, grows corn, wheat, pinto beans, and peas on his land. Like many farmers, Townsend depends on the aquifer to irrigate his crops, especially during times of extreme drought.
This country is about weather, and right now it's sure not going to.
Today's irrigation technology is able to pump out water that has been in the aquifer for hundreds of thousands of years in just a matter of minutes, a rate which far outpaces how fast nature can replenish it, threatening the overall sustainability of the aquifer and agriculture.
This well over on the southwest was right at a 2,000 gallon minute well, and now we're getting around to about 600.
According to the Kansas Geological Survey, groundwater levels in the aquifer have dropped an average of 14 feet since 1996, about a foot a year. Aquifer drop rates suddenly doubled, an average of 2 feet a year between the start of 2011 and the end of 2012 alone.
Since about 2011, there's been a significant drought, and this is really across most of the High Plains Aquifer, but this area, as well as others, you're now in a period of extreme to exceptional drought.
Dave Heineman, a hydrologist at Michigan State University, is leading a team of scientists funded by the National Science Foundation that is studying the aquifer. The team is analyzing data from as far back as the 1800s on changes in climate, irrigation technology, and water policy to build models that could forecast what the future holds for the aquifer and for farming.
When we feed the climate into these models, we're able to predict what happens with the water levels. And as long as you have pumping data, you really get a great understanding of the system.
One of the reasons why the aquifer replenishes or recharges so slowly is due to the water cycle itself. When precipitation in the form of rain or snow hits the ground, some of it runs off. Some evaporates back into the air from the ground, or is transpiration from plants. What doesn't run off or evaporate slowly seeps down through the soil and its layers by gravity in a process called percolation. In western Kansas, it can take 1 year to recharge the aquifer by less than an inch.
There's not enough recharge out there, not enough precipitation.
During the drought of 2012, Mitchell Ballman, a 4th-generation farmer outside of Hoxie, Kansas, was able to maintain his crop yields only by pumping more water out of the aquifer.
In 2012, we were drastically impacted. I mean, it affected our crops, definitely affected the aquifer. We depend heavily on the Ogallala, which is what we're pumping up for our pivot irrigation.
Now, in an effort to extend the life of the aquifer, Ballman and other farmers have started a grassroots effort to cut back pumping by 20% over the next 5 years.
I think we're averaging probably 2.1 foot a year is what we're dropping. That's why we're looking ahead to the future to try to promote saving, being proactive instead of reactive.
But sustaining the Ogallala aquifer and Kansas agriculture must also include more scientific research. Hyman's team is working with local and state government officials, water policy experts, and farmers to develop a long-term model for aquifer water use based on more precise measurements of precipitation, percolation, and natural recharge, better monitoring of agricultural pumping, and forecasts of changes in climate and population.
To do anything about sort of forecasting what happens in the future, we have to work with both the farmers and the policymakers, because as we do these scenarios of the future, we have to have a pretty good idea that the scenarios we're running are feasible.
We've got to start someplace. We've got to get this thing moving. It's too important.
Improving water policy and reducing water usage are not only key to sustaining the Ogallala aquifer, but also to maintaining a way of life in western Kansas and across the entire High Plains region.
Okay, so water table. This is what they were kind of a recap of what they were talking about. It's recharged by rain and snowmelt and soaks into the ground. It seeps in from ponds, rivers, and lakes. It's discharged by humans pumping it, evaporation and transpiration, that evapotranspiration she was talking about. And it also, the groundwater refills our ponds, rivers, and lakes. Even in the winter, our rivers continue to flow from groundwater. That video was about, I want to say, done in 2013, so about 7 years ago. And obviously, we've had a lot of rain in the last 2 years. But it still takes, even with the amount of rain, it's not going to recharge as fast as they were pumping it out, because it takes a lot of time for that amount of water to percolate through. And a lot of it just runs off through the rivers and streams. Now, hopefully it's recharged pretty well in the last little bit. And when we're talking about that and we're looking at this zone of saturation and zone of aeration, which means this is filled with water and this is filled with air spaces, where we have a depression and you have this zone of saturation, water seeks its own level, so it will flow through and fill in that lake. Lake Minnetonka has groundwater coming into it. A spring, if you find a spring in a lake, that's groundwater coming in. Now, what's interesting, if you happen to have a well on your property, there's this thing called a cone of depression. And what happens is you actually, as you start to, you might start out with water table here, but as you flow all that water into it, you actually get a cone-shaped depression. And so you always have to have a little deeper in for your piping to make sure you stay in this zone of saturation and below the cone of depression, which is a depression of, so this is zone of saturation. And while this is a zone of aeration, you create a cone of aeration farther down below where the water table should be. So again, just a really quick recap. If my water level's here, this would be a regular, it's our water table. Down here would be an artesian well because it's got two confining layers, and this flows under its own pressure. There are all types of wells. I mean, you can think of Jack and Jill running up the hill in the crank well. Well, ironically, those wells are still used all over the world. When I was younger and we had our property, we had one of those old-fashioned cranks that you saw from the 1800s, kind of a modification of what she has here. This is not uncommon around the world to still get groundwater up that way. Spring is a naturally occurring place where water flows from an aquifer or groundwater to the Earth's surface. So if I look at this one here, on an average day, nearly 303 million U.S. gallons of water flow just into the Big Spring in Missouri at a rate of about 469 cubic feet per second. That's just one spring, and think how many springs there are in your area, let alone the whole state of Minnesota, and then the whole country.
With its rugged snow-capped mountains, clear freshwater lakes, and massive sequoia trees, The Sierra Nevada mountain range in California is one of the most visually stunning landscapes in the United States. In addition to its beauty, snowpack and snowmelt from this 400-mile stretch of mountains serves a purpose, providing drinking water to about 30% of the residents in California, irrigation water to the more than $35 billion a year agricultural industry in the San Joaquin Valley, and water to run the hydroelectric power industry that supplies at least 15% of the state's electricity.
In California, we wait with bated breath to hear about the size of the snowpack. In recent years, our precipitation patterns have been changing, with maybe less precipitation during the wintertime and a little more precipitation in the springtime. It's so nice to see this put together. How's it going to help solve the water balance for the mountain?
Martha Conklin is a hydrologist at the University of California, Merced, and is supported in part by the National Science Foundation. She belongs to a team of scientists that studied the Sierra Nevada snowpack to make more precise measurements and predictions of snowmelt and runoff, so the water can be better managed.
This one has a tensiometer.
We'll come up with information systems that are going to be useful for better water resources decisions. We actually provide knowledge to the state of California on how it's going to meet the change in snowpack and how to adapt our water management systems to do that.
Following the Earth's water cycle, water precipitates as snow over the higher elevations of the Sierra Nevada from November to April, accumulating into a thick snowpack.
That basically provides free water storage for us for 6 months of the year, because that water that falls as solid precipitation just sits up there.
The snowpack remains intact until the weather warms during the spring and summer months and generates snowmelt. The water then moves slowly downhill before it ends up in streams and rivers as runoff or percolates into the soil as groundwater. But warming temperatures in a changing climate cause more water to precipitate as rain rather than snow. This rain never accumulates as snowpack. Instead, runoff occurs earlier, potentially leading to water shortages later in the year. Tom Harmon is an environmental engineer and lead scientist for the Water Sustainability Project at UC Merced.
We've relied a lot on past history to try to judge how much water we'll have, and statistically that used to work out. But now that climate change is changing those statistics, and we can't use the past as a very good predictor anymore.
Harmon, Conklin, and other scientists are conducting research at the Southern Sierra Critical Zone Observatory, or CZO, located near Shaver Lake, California. The data from this observatory is used to understand snowpack accumulation, its water content, and melt rate. The information is then used by many water management groups throughout California to help better manage dams and water release schedules.
I think now the next challenge is how to put together that data carefully, accurately, and connect it with a theory that makes sense and covers all the processes in sufficient detail that we gain predictive capabilities.
So we have these at different depths.
To more accurately measure snowpack, the Southern Sierra CZO has developed a system of wireless sensors strategically clustered around several watershed locations that collect data in real time.
We're measuring precipitation, distribution of precipitation as snowpack, and how that snow melts and goes into the soil, what our soil water content is, and how the water actually moves from the soil into the stream.
In addition, a network of flux towers that soar to more than 150 feet high measure fluctuations in the atmosphere that quantify the net rate of water exchange during evapotranspiration, or the water from snowpack vegetation and the soil that moves into the air, thus removing water from the critical zone. By collecting this data, scientists can provide information that can help determine not only how much water will be available, but when and where it will be available.
We look at what we can do with developing better information about the snowpack is to provide information to decision makers that they can make better decisions and know how much water is available in the system.
Knowing where the snow is and how much runoff and river flow to expect in a given season can provide the information necessary to help water managers allocate water resources for people, agricultural, environmental, and industrial needs.
Okay, so remember that permeability thing that we were talking about? Different parts of the country have different substructures, if you want to say, underneath the ground, basically different bedrocks. And if you have a limestone called karst, which we do have, and you'll notice it here, in kind of the southeastern Minnesota, southwestern Wisconsin into Iowa, a lot of it in here. This is all karst topography, which means as water comes through, it leaches some of the lime away and you can get sinkholes. And so as waters come in, they actually pull some of the lime down and you can actually get big underground caverns, otherwise known as, when they drain, caves. And this is one farmer's field, you can actually see sinkholes where, as this loses its water, sometimes then it actually collapses and you get a sinkhole. You can actually get trees that are kind of at the top, they're growing, they just fell down. And you can get whole cave systems under places. And so this kind of looks like what happens. You get your stalactites are tight to the ceiling. Stalagmites are the mighty ground, so they come up from the bottom. And if they join, they're actually called a pillar. And so as this gets eroded away and then the water goes away, or it just loses enough surface structure on the top, the rock you can get a cave in and you can get a sinkhole. And sometimes those sinkholes aren't just that little hole. They can go much, much farther. As this house sadly was discovered, Florida has a lot of sinkholes because as they pump their groundwater out, the spaces in between the sand and all of that start to collapse and you get sinkholes. And they say there's a good chunk of the state that's actually positioned over a sinkhole.
Anderson Cooper 360, weeknights at 8 and 10 on CNN.
It's just a few short steps down to an incredible underground site.
And this was the original cavity that eventually collapsed in.
A massive sinkhole carved out of solid limestone by drops of water.
So this is what a sinkhole looks like from the inside.
From the inside, yes, before you fill it up with sand and dirt.
And if someone were living right on top of this, they'd be at risk.
Yes.
Geologist Jerry Black says Sunshine State homeowners might be surprised to find out just how common these are.
What are the chances of someone having a house in Central Florida and living on top of something like this?
Very good. Not as probably as close to the surface as this, but you definitely have cavities of this size all over the state of Florida.
Fossils found in this sinkhole show it's been around since the Ice Age. But no different, Black says, than the sinkholes we see opening up today. These are just a few of his pictures. The one thing they all have in common is water.
Rainwater is going to turn into groundwater, and that's what's naturally acidic. That's the device that dissolves the limestone and will help create these cavities.
What is unusual about this sinkhole? It's easy to get inside. Called the Devil's Den, it's open to tourists for viewing and diving. Dive instructor Prince Johnson takes me under for a look. I find that this seemingly placid pool of water is anything but.
The water has gone down considerably because of the aquifer, but it's also risen when we've had hurricanes and tropical storms. It has risen another 45 feet.
45 feet?
45 feet.
So the water's constantly going up and down?
Up and down.
Depending on drought or hurricane.
Right.
Down here, it's easy to see how fluctuating groundwater has silently wreaked havoc. I passed by limestone boulders as big as cars sitting on the bottom. And these same forces are still at work, compounded by the demand for fresh water.
It is progressively dropping yearly. And that's basically over the whole state of Florida. The aquifer is getting lower and lower.
Perhaps most striking to me, how appearances of this sinkhole are so misleading. A single beam of sunlight reveals the cavern is even bigger below the waterline, with tunnels and passageways carved deep into the darkness.
It's incredible to see like that, David. I mean, do you know like how deep that one is, and also how many there are in Florida?
Well, there are thousands across the state of Florida, literally thousands that pop up every single year. The state keeps a loose track of them. People call in to report them when they happen. But think about this. We were talking about how deceptive these things are when you look at their size. There's much more to this cavern below the water level than there is actually up here where I'm standing. But look up here up top. The hole that opened up when this sinkhole was formed. You see the size of that. Now you see how deceptively large this whole cavern is underneath it. So when you see a sinkhole opening up on the surface, there's so much more going on down below that we never see.
So this is a video, if you want to go back and watch it, about cave formations in Australia. And this one is even a little bit longer, and I'm not going to show it. You're going to have to go watch it if you wish. This is on some more cave water usage across the whole country. Thank you for watching.